Welcome everybody to the second colloquium of the Computing Colloquium series for this fourth semester. My name is Andreas Goetz. I'm a faculty in chemistry and I'm the chair of the Computing Colloquium. So I'm also the one responsible for the Colloquium Canvas page. And today is my great pleasure to have Andreas Goetz giving us a presentation of some of his computational and chemistry work at San Diego Supercomputing Center. I invited Andy to give two seminars today. So this is the first of two. He is also presenting in the main campus, the material science and chemistry colloquium at 1:30. So if you really like what you see this morning and want to get more of it, please join us in MCMR 205 in the afternoon. And that seminar is going to be more about the applications. When I had to pick a speaker from my field of research to present to the computing colloquium, I purposely picked someone like last year that works more on software development and not just on applications. And this is hard to find especially in the US. I think it's a bit more common in Europe. And so I think Andy is a great example on how you can do really advanced research by developing and improving computational software. And Andy comes from Germany. He trained, did his undergrad in Erlangen and the Ph.D. in Erlangen. And then he moved for a postdoc in Amsterdam, where he worked on a code called Amsterdam Density Functional, IDF, which is a commercial, widespread simulation package for quantum chemistry. And then after Amsterdam, he moved to San Diego as a postdoc and decided to stay there for 16 years. And now he's a research scientist still in the San Diego Supercomputing Center. And I think his main work is really about making, improving computational tools for computational chemistry and biochemistry. He has worked on AMBER, which is one of the most widespread computational programs for molecular dynamics simulations. And now he's working on a new GPU-based code that does quantum chemistry and QMMM calculations. Right. So I'm sure we'll learn more from him in a few minutes. And thank you again, Andy, for joining us. Okay.
Yeah. So thanks, Oliviero, for the nice introduction. Thank you, everybody, for coming. This is a nice big audience. Sometimes you go to Colloquia and there's only a handful of people in there, so it's actually nice that there's so much interest. Maybe some of you are forced to be here, so I'm not entirely sure, but food. And there's some food, right. So I think Oliviero has given a nice overview of what I'm going to talk about. One other thing that I do at SDSC is also I'm involved, and I don't do user support, but I very much like working with all the people who actually also design the supercomputers. So I'm also involved in one of our systems, and I help porting and optimizing some of the other codes, although my main interest is chemistry-related simulations and biomolecular simulations. And so what I'm going to try to do today is I probably have too many slides. I might skip some of them. So if there's any questions in between, please let me know, because I have about 45 minutes. That's what I understand, but I might have too many slides. And I want to give a little bit of an overview of the hardware and some of the hardware developments, then on how you actually program GPUs. Who of you has programmed GPUs? Okay, so we have a few people who actually know about that. For the other ones, maybe that would be interesting. And then I'll talk a little bit about the software and what we have achieved with that software. And so Oliviero has given a little bit of a background. I just put over the slide. There's a little bit of my research interest, and it goes from molecular simulations to the corresponding method and software development. It's something that I've been always interested in, and I hope that I can give you a little bit of an overview of that. just as a background to where I'm from, I'm University of California, San Diego. So the San Diego Supercomputer Center is one of the, what we say, big institutes for scientific computing at UC San Diego. UC San Diego is one of the 10 campuses of the University of California system. And we have at UC San Diego about more than 40,000 students. So it's a pretty big research university. And so here's the campus. Down there is La Jolla. San Diego downtown is somewhere here. And if you go a little bit further, there's the border to Mexico. So on Wednesday, I've just been down to Mexico. I actually took the trolley down to the border, walked over the border, and got picked up by some colleagues. I was on a thesis defense of a master student I was supervising in Ensenada, which is not too far from us. So it's a pretty international community. This is the famous Geisel Library. So that's pretty symbol for UC San Diego. The Scripps Pier is down here. The Scripps Pier is part of this Scripps Institution of Oceanography, and some of you might know it. It's pretty famous for the Keeling curve that has been established there. So basically the CO2 measured since the 60s, how much CO2 we have in the air and how that, increases due to the industrial processes, burning of fossil fuels essentially. But they do lots of other interesting research. SDSC has been established 40 years ago, 1985, as one of the first national supercomputer centers by the US National Science Foundation. It was later integrated into the UC system, so it was outside of UC San Diego. It was run by General Atomics, which is right across the street. And General Atomics is a very interesting, if you ever get to visit, you can get public tours. They have a fusion reactor there. So it's actually nuclear fusion GA. So there's a D3D fusion reactor, which is pretty interesting to see. And last year, the School of Computing was established, School of Computing, Information and Data Sciences. And SDSC is one of the departments. The other department is the Habichulo Data Science Institute. We have about 250 people, and out of those are about 100 researchers. The other people are, support staff, administration, user support, etc. And we are primarily funded through research grants, but also sell services to industry. So people need to keep funding. And so when it was established in 1985, so over the years, there have been many different types of supercomputers. So the Cray XMP in 85 was the first one. And, all sorts of different types of architectures from, vector supercomputers to massively parallel systems. So massively parallel systems, nothing new. People have had these ideas in the past. This system you might know from Jurassic Park, was used because there's so many nice blinking lights. It was used as a feature in the movie to show some of the computing that is being done. Yeah, if you're a computing geek, you might be interested in some of these things. Now, if you compare what we had in the past and what we have now, is so in 1985 there was a Cray XMP. That machine had 800 megaflops, so floating point operations per second computing power, but out of 4 vector CPUs. Our main supercomputer that we run for NSF now, the National Science Foundation, is called Expanse. It was called in 2020, so it's not so new anymore, but it's still quite a useful system. It had both CPU and GPU nodes. It gets about 5 petaflops from AMD EPYC CPUs and NVIDIA V100 GPUs. And so that's about 6 million times faster in terms of floating point operations than the first machine. So you can see that, how the hardware has developed and how that enables us to do a lot of interesting science nowadays. Just this year, we put into operation a testbed system. So this is not open for allocations yet, but it's basically for us to learn about this system. It's an HPE Cray system. I'll talk a little bit about this. This machine has 10 petaflops HPC. So really, when I say HPC, I mean 64-bit floating point operation performance. And so it's actually twice as powerful in principle as entire Expanse, but it's much smaller. So instead of, I don't know actually how many racks of hardware we have in Expanse, but that machine is just in a single rack, which I always find quite interesting. So just a few years of development and you get this performance increase. And just this slide I like to put up just to think about it. So we usually program for CPUs GPUs, but particularly if you're in computing and computer science, you'll know about other special accelerators or FPGAs. There's ML, machine learning, AI special hardware. So there's different types of accelerators that are being developed to for different applications and compute workloads. And we actually have one computer that's specific for AI acceleration as well at SDSC. But what that also means that computational scientists need to develop algorithms and software that actually can make use of that hardware because that hardware looks different. And you need to think carefully in how to structure your algorithms to get performance out of these different computing hardware. This is a slide I like to put up to just motivate, where the current multiprocessor, multi-core, and then massively many core systems have been coming from. And you're all familiar probably with Moore's law that the transistor count in integrated circuits doubles about every 2 years. And so if you look at this slide here, it's taken from this website by Carl. So I didn't make this, but I like to talk about it. That exponential growth here in yellow, you can see, so with time, the transistors are still increasing. What happened is you look at the clock frequency here is in green, so about the mid-2000s, it's been leveling off. So when I was a graduate student, we had single core CPUs and you just waited and the clock frequency went up and then hooray, my code runs twice as fast and I don't have to do anything. It's just like beautiful, right? You don't really have to think much about new algorithms. That's not the case. I mean, there's still improvements, of course, being done also on single core, single threaded performance. But you see that that's leveling off essentially. But what happened is the number of logical cores has increased. So we have, many core processors. And so the performance increase really is mostly due to the increase of CPU cores per processor. And what that means, you really have to think in how to write parallel code and not just serial code. And these are very outdated slides here, but it gives you, the essence of this still holds. So what you see on the left is the floating point performance for FP64 operations. And on the right, you see the corresponding memory bandwidth. And GPUs have been outperforming CPUs since quite some time in that, both flops and memory bandwidth. And so memory bandwidth in particular is very important. People always talk about flops and so on, and I'll show you some other slides about, we have the fastest computer and so on. But what does that actually mean? Because many and probably most algorithms nowadays are memory bandwidth bound, or you very quickly hit memory bandwidth limits. So you can have the fastest, processor fastest, but if you can't get the data to the processor to compute on, then it's not going to run faster, right? All this development has been driven in GPUs, in particular, initially by the gaming industries, which is a $100 billion business. And now it's the AI industry that has been exponentially growing and exploding. And so we really have to just use whatever industry throws at us, because it's not us who is funding the main development of this. Us, when I say us, it's scientists, researchers at universities, right? So we have to work with budgets of, NSF budget was 9 billion, NIH budget about 47 billion in fiscal year 24. So that's much smaller than what industry is throwing at developing or using the systems. And so that's where, people make decisions on how to design the chips and architectures. And GPUs are very good at data parallel computations, matrix algebra, and quite well suited for deep learning workloads. So that's why they are used extensively there. I just want to motivate you a little bit also about thinking about these developments. So if you look in 2001, the number one in the top 500 list. So the top 500 list is a list that is of the fastest supercomputers in the world. So there's submissions about specific workloads that you have to run, and then you can show what is the performance that you get. And so this was a machine that covered the entire data center at Lawrence Livermore National Laboratory, and it got 12.3 teraflops. So floating point operations per second. And SDSC expands, like I told you. So this machine cost $110 million in 2001. So pretty expensive, right? SDSC expands cost about $10 million, and that was in 2020. And like I said, you have an aggregate of about 5 petaflops. And this is data from 2020 nowadays as well. The cost of gaming GPUs keeps changing, but you can maybe 4,000 is not right, but make it $8,000. You can build a box that has 4 GPUs, and that gets you FP32 performance, with 32-bit floating point numbers, about 120 teraflops. So that's 10 times as much as this ASCII-wide system. So you have a lot of computing power available nowadays. So do something great with it. That's what I always like to say. Your iPhone is more powerful than what I was doing. What I had available when I was doing computations during my Ph.D. So there's no excuse not to do cool science with it. Expanse, just let me talk briefly about it. It's the machine that we have. Maybe I'll skip quickly over this, but we have 208 GPUs in that system, so it's not very huge, but it's good enough. It has a lot of use for research, and of course these systems are built in such a way that you have the compute nodes, but then you have also some I/O nodes, and then you have some data storage systems, because it's very important to store the data and have fast local I/O as well. Talk a little bit more about, this is how the compute nodes look like. So for people who don't know that maybe, these are the GPU nodes. So here you see the GPU sitting in the system. They are actually not something that goes in the PCI Express bus. So if you build your own systems, you might know that, but some people still do this nowadays, your own workstations or gaming desktop. These are actually like processors, the data center GPUs that go onto the motherboard like a CPU. And so here you see the coolers, and you have like 4 of those GPUs sitting in there. And what you see here behind, those are the coolers for the CPUs, and then here's the RAM and so on. And these just go into the data center. So what's important about these systems is that you also have fast interconnects between the GPUs. So if you need to parallelize your code not only within a single GPU, so I'll tell you, so you have massive parallelism within a GPU, but then you need to scale out across multiple GPUs. When you do that, you need to communicate between the GPUs. Your code program must communicate, right? So typically you implement this with MPI. And in order for these communications to be faster, there are special interconnects that every hardware vendor has their special interconnects. Like NVIDIA has something they call NVLink, and so you have like these special interconnects where the GPUs can talk to each other without having to go through the CPU, and that they're connected to the CPUs via the PCI Express bus. That's how a compute node looks like, and I'll talk a little bit more about Cosmos. Cosmos is the new system that we have, and it's basically really the single rack here, and there's something else glowing here, so the light's just installed for it to look fancy, but that's where the fast I/O, so the vast file system with very fast high I/O operations connected to the system, and then there's another racks for actually the large-scale data storage, where people need to store data they produce or want to use and have processed on the Cosmos system. And that rack, how it looks like. So what you can see here, I'll tell you a little bit about it because I find it interesting. I hope you find it interesting. Has like 3 of these compute chassis, and so one of these compute chassis has 7 compute blades. You can see those here. So if you count them, there should be 7. It might be 8. I don't know where I took this picture from. Depending on the hardware you stick in there, you can purchase this with different CPUs and GPUs. You can put up to 8 blades, compute blades in there. And they provide for power. And what you see here is the liquid cooling. This machine is entirely liquid cooled. It's really nice if you go in the data center because it doesn't produce any heat. It doesn't, it's not noisy. There are no fans in there because the data center is really noisy with all the fans that we have running in there. So the liquid cooled system is really nice. And then, of course, the network fabric. And then one of these compute blades has actually 2 compute nodes. And each of those compute nodes has 4 sockets. So there are 4 APUs in there. Now, I'll tell you a little bit more what an APU is. It's an accelerated processing unit. AMD calls them like this. And it also has these slingshot interconnects, which is a special high-speed networking system from HP. And then local SSDs for fast I/O on the compute nodes. So if you have scratch I/O that you need that goes beyond what you can put into RAM. And then our overall system configuration is 42 nodes. So there's 168 APUs in total in that single rack. And what you see down here is actually the CDU cooling distribution unit. So that cools the system. So you have the liquid cooling. So the cold water comes in here, cold liquid, hot liquid comes out the red pipes, and then it goes down to the heat exchanger. And the heat exchanger is cooled with water that comes from campus. And then the hot water goes out. In our case, we have some cooling towers where we distribute it. Some data centers reuse that heat because, you could heat the building in the winter, for instance. It's not something we have to do much in San Diego, fortunately, but maybe here it gets a little bit colder. That could be put in place. But of course, the infrastructure needs to be put in place. Our data center is old, 40 years. There was no liquid cooling. I mean, that's not true. There was no liquid cooling, but it's very different. And mostly most of our systems are air cooled, but so we're retrofitting the data center, and I don't know of how many megawatts of power we can go. This machine itself draws 140 kilowatt, so a lot of power that goes into those systems. And so the maximum capacity that we have is actually limited, or that we're building out is going to be limited by the amount of water that campus can provide to the data center. So it's not anything else. This is how the single node looks like. It's similar to what I've shown you before from the NVIDIA system. So you have these APUs sitting on the compute node, and they're all interconnected. In this case, it's AMDs, high-speed, bidirectional, it's called the Global Memory Interface, Accelerated Global Memory Interface, XGMI, they call it. But yeah, so that's basically how it looks like. And then you have the NVMEs connected, and you have the networking goes out here over the PCI Express lanes. And that's the APU. So this is a diagram of the APU. So APU stands for Accelerated Processing Unit. And so what it does, it's quite unique. It combines a CPU and a GPU and a memory on a single package. So if you look at this, so you see here, this is HBM3. This is the high bandwidth memory. So this is a special memory that provides high bandwidth. And it's sitting right on the chip. So there's 100 gigabyte of this memory. And then what you can see here is there is like 3 of these 8 CPU core chiplets. So it's a total of 24 CPU cores. And these are what AMD calls accelerated compute dies, XCDs. So those are basically the GPU processing units. So there's in one of those 228 vector and matrix GPU cores. Okay? And so there are 6 of them. AMD also produces pure GPUs, where instead of these x86 compute cores, you just have more of these GPU chiplets. Now, why is this interesting? This is interesting because when you have a CPU code and you want to accelerate it, what people say accelerate it, so basically offload some of your computation onto GPU, there's several ways of doing that. But typically, so you have to transfer the data to the GPU, and then you have to do some computation there, and you transfer it back to the CPU. Meaning, you transfer it to the GPU memory, forth and back. And that is a bottleneck in itself. And so when you start porting a code and you look at your hotspots, what is the most expensive part? And some of the codes are very complex, right? You might write a small code, but some codes like Amber or Quick, they have hundreds of thousands or even millions of lines of code. And there are many different algorithms that have to all run efficiently. And so if you introduce something with a high latency in between, you can destroy the performance of the entire code. And so it's sometimes not a week or month, but year-long effort to actually port this. While, if your code actually, everything is in the same memory space, you can accelerate portions without having that bottleneck. So this makes it potentially, and so we are investigating this easier to port codes from CPU to GPU, or have piecewise accelerations over time without having this frustrating period in between where you have a very fast kernel that accelerates part of the code, but overall your time to solution is lower. Now, how does the current HPC environment really look like? So I talked about some of the systems that we have at SDSC. These are the biggest machines that we have for at least publicly available and known, the DOE, Department of Energy, exascale supercomputers. Really, these ones are El Capitan, looks like Cosmos. It's just much bigger. Has APUs. Aurora is Intel based, has Intel CPUs and Intel GPUs. And Frontier is AMD based again, has CPUs and GPUs from AMD. Here we have Intel CPUs and NVIDIA GPUs. We also have this Voyager system, which has Intel Habana AI processors. So this machine literally runs only PyTorch and nothing else. There's a CPU on that node as well. So the Habana processors, they are just accelerators. But you have a few CPU cores, and then it's like a CPU plus GPU, but instead of a GPU, you have this APU. And it's similar to Google has tens of processing units, etc., etc. There's lots of companies who are developing these accelerators for AI. But really, all of these systems are highly parallel. Distributed memory machines, so you have to program them with MPI plus OptMP, and or some other language to accelerate your code on GPUs. And that's basically how the systems look like. And this is the top 500 list that I was talking to you about. This is a slide I grabbed from Jack Dongara, actually. And you see, 1997, we reached a teraflop in terms of computing performance. It took about 11 years to have 3 orders of magnitude improvement. So, getting from a teraflop to a petaflop, right? So from 10 to the 12 to 10 to the 15 floating point operations per second, peak performance. And then it took another 14 years to get to an exaflop. So it becomes more and more difficult to do that, right? It's actually really hard to build these systems. And the other question is, of course, what is it good for? Do we need that, right? It's interesting to make these hero runs, and it informs future hardware and software developments. But in terms of practical applications, this is another slide I have from Jack Dongara. Here's a ranking of the fastest supercomputers. This was 2022, so it's changed a little bit, but the essence is still the same. And this is the top 100. This is basically the benchmark that people use. That's HP LinPack. That's effectively just matrix multiplication, right? And so that's relatively trivial to parallelize, right? And scale out. It's still hard to do, but you can see, they are getting here, this exaflop, right? 1,102 petaflops. The ranking here now is different. The ranking here is according to a high performance compute conjugate gradient benchmark. So conjugate gradient algorithm is very different from this matrix multiplication. And it's much more similar to what practical science applications actually do. Most of what you do is not just matrix multiplication, right? So you need to solve some partial differential equations or something similar. And this is the performance, the peak performance that you get. And so you see the fastest computer is actually not the one that has the highest HPL performance. The other thing that you can see is that HPCG gives you, in the best case, 3% of peak, right? So it's like basically, buying a Ferrari, and instead of being able to drive 200 miles per hour, you can only drive, say, 2, 3, 4, 5 miles per hour, okay? So that is a little bit of a perspective when people tell you, which are the fastest supercomputers and what is an exaflop, exascale computing and so on. It's actually really hard to do. And programming these GPUs efficiently and scaling out in particular is very difficult. So let me think about this. I don't see my what I see now is my slides, and I might go over some things quickly. How much time do you have? I have because I want to talk about the software that's developed. 20 minutes, okay. But just very briefly, comparing GPU versus CPU is, if you have the same real estate in terms of like silicon, on a CPU, you have many less compute cores, but they have much more sophisticated hardware with multi-level caching, prefetching, batch predictions, and whatnot. And the GPU has more, say, thousands of simplistic compute cores, if you want to call it cores, but they are basically packaged into compute units that are vectorized. So they operate in lockstep. And so you have vectorized loads and stores to memory, and you need to manage the memory hierarchy a little bit more yourself, or think about it at least than on CPU. On CPU, you should do the same with good performance. And this is the GPU architecture. So you see one of NVIDIA calls those streaming multiprocessors. This is from 2009, long time ago, that's when I started to look at GPU programming. The basics of that has not changed much, so that's why I still show this slide. So you have this multiprocessor which has basically these FP32 compute cores or also FP64 compute units and some special function units and instruction cache, of course, sitting there shared, and then there's like shared memory and data cache. And these operate in lockstep, so you have to program in such a way that your code operate in lockstep. And that you also have memory accesses that are coreless, so that you actually have not random threads that are sitting next to each other actually access different memory locations, because then your code will have very, very bad performance. But what the GPU is very good at is handling many more threads than processing cores. So the way you do this is, I probably have this on some slides. Don't want to go into details, but the GPU is very good at doing that. Then you have these tensor cores that you might have heard about. I have not really used them. I'm not programming with them. I just want to talk to you about. So those have really been developed mostly for deep learning applications, because you have these, in particular, deep neural networks have fully connected or linear dense layers, convolutional layers, recurrent layers, and so on. But all of these boil down, or many of those operations boil down to some matrix multiply and accumulation. So you have basically matrix multiplication between matrix A and B, and then add that to some previous results and store this back, and can do this with mixed precision. And these are super fast for deep learning applications. Or there's also linear algebra libraries. I think NVIDIA has very nice QBLAS, so BLAS linear algebra system implementations that actually make use of tensor cores and mixed precision and so on to get the highest performance out of the hardware. This is a diagram of the V100 GPUs that we have on Expanse. It looks very similar, like I've been showing you before. You have no tensor cores on there, and you have these compute cores. Not much to talk about in principle. The way you program these things is NVIDIA has CUDA. It's a proprietary language that works for NVIDIA GPUs. It's de facto standard for high performance code. And then there's HIP from AMD. That's an open source version, I want to say, similar to CUDA, basically. In some sense, AMD has been copying NVIDIA with that. So you can write code with HIP that practically looks like CUDA, and it can work with CUDA's runtime, and then also AMD's ROCm runtime. But really, if you have code like this, and that's what we're doing in our software, we basically have 95% of the code that looks the same. And then there's just some pragmas, to use either, we basically have include files to use, instead of using the language for the function calls for specific for CUDA or for HIP, we just call it GPU, something like GPU allocate and deallocate. And then depending whether we have the CUDA code or the HIP code, we just, compile one or the other, but it's 95% of the code is the same, and then there's 5% that's different, where some special features are implemented in CUDA that are not available in HIP to get the best of the performance. Yeah, and then there's OpenCL, SYCL that Intel likes to use, but Intel is not in a good place right now, so we don't know what's going to happen with their GPU roadmap. And you can use OpenACC and OpenMP as a directive language to also program GPUs and have automatically generate kernels. And the way a GPU program works is, you have your CPU code, and then the CPU code initializes the parallel kernels, the code that is running on the GPU, and then you have the CPU code running again, and so on and forth and back. And so if you look at this in terms of your host and the device, you have the CPU and you have the GPU. You copy the data from CPU memory to GPU memory. That goes away if you are on an APU. You don't have to do this anymore. But if you have a GPU attached to a CPU, you have to do that. You load the program, execute it, and then you copy the results back to the GPU and do your I/O. And so what you write are these GPU kernels there's code that executes on the GPU and operates in lockstep, so-called SIMT, so single instruction multiple threads, where the threads get mapped onto what effectively is the SIMD architecture on the GPU. And so on each of those threads here, so you write a kernel that looks something like this, where you can so this gets executed in parallel on the GPU, and then you tell the GPU basically when you launch the kernel how many blocks and how many threads you're using, and a block is basically a group of threads, and that group of threads runs on a single of these multiprocessors that I was talking about before. And so you have multiple blocks, one goes onto one multiprocessor, one on the other, and so on. And that's on a very high level view. So this is basically, so you have this block, and then in this block you have all these threads, and they get actually executed in terms of what NVIDIA calls a warp, or what NVIDIA calls a wavefront. And here you can see what happens basically. So you launch this kernel. For instance, here's an addition of a vector B plus C, storing in result A. So thread 0 basically works on index 0, thread 1 works on index 1, and so on, and thread N will work on index N in the array. And so that's how you basically can parallelize, right? So this is a simple example about, vector addition. And the kernel launches are asynchronous, so you can launch a kernel and then you can do something on the CPU, and then you can launch another kernel. And what you have to do here is to avoid a thread divergence or branching within a warp. Like I said, these have to execute in lockstep. So if you have if statements in here, if it's not just a simple addition like here, you have to have an if statement in a way that ideally all the threads will on one of those warps execute the same branch of that if statement. If thread 0 wants to do something and thread 1 wants to do something else, right? Because, say you have something like if I'm working on atom 1 and I'm working on atom 2 in my molecular simulation, right? Then there's going to be some thread divergence, for instance, right? Or if so you have to make sure that that doesn't happen. Otherwise, it will completely destroy performance, because then the execution will become serialized. So thread 0 will do its work, and all the other threads have to wait. So literally, they're masked out because they have to do the same operation. And let me skip a little bit about that, because otherwise I have probably not enough time to talk about actually the applications that we've been developing. But you have to think a little bit about, the memory spaces as well. I said, we have the host and then we have the device on which the grid of blocks of threads executes. And it's a little bit like, a thread cache blocking on CPUs, and you can do that on GPUs as well. In addition to that, you have to make sure that you have more or less memory accesses. So that's actually very important when you read and write to the GPU global memory. So the GPU has its own memory space, right? And that memory space cannot be accessed by the CPU except, by copying data over by the corresponding functions of the API. But I'm happy to talk with people about that afterwards if you're interested or want to know more. So for biomolecular simulations, the interesting piece, I've been talking a little bit about computing history, and the science that we are doing and the algorithms that people develop has very much gone often, or still has over time, and still is going hand in hand with the hardware developments, right? So, and there's often a lot of like excitement, you see, oh, there's new hardware, supercomputers coming out, we can do all these great things. And then people get excited and then they realize, okay, well, at the end of the day, our simulations are still too small or not, fast enough and so on. And sometimes people get disillusioned and so on. And with the GPUs, I think for biomolecular simulations in particular, there was a lot of interest there's been computing GPUs and in particular in chemistry. So for chemistry related to 2013, there was a Nobel Prize in chemistry for multi-scale simulations. Effectively, the QMMM developments. And now, everything is exciting, of course, about AI. There's lots of use also in chemistry and biochemistry sciences. For instance, AlphaFold, ESMFold, I think is from Meta. Lots of companies that are actually investing in that because they see that, well, we can do lots of useful science that is useful for pharma industry or other things, or materials, for materials development and so on. So there is also not just academic interest, but a lot of industrial interest because all these applications, there's practical applications for all of this. The code I developed is Amber, or one of the codes, and Amber is two things. One thing is a set of force fields. A set of force fields basically describes the interactions between the atoms that make up the molecules, and molecules can be something small molecules or something small like water or organic molecules, but also proteins and enzymes and everything that we are made of, right? So everything we're made of is basically, at the end of the day, molecular physics, if you want to. So we can describe proteins, DNA, lipids, carbohydrates, and so on. And then there's a molecular dynamic simulation package that is also called Amber. So that sometimes leads to confusion. So it's both the force field, so the functional form and the parameters, but also the simulation package. They're not necessarily connected. So Amber also supports different force fields. And it's been around for some time. So some of the code is pretty old. And so there's lots of old Fortran code in there. Fortran C, C++, Python, CUDA. Yes, somebody loves Fortran. I love Fortran. I think the world would be better if we only had Fortran, but that's just my opinion. Yeah. No, I mean, yeah, Fortran is still great and has a lot of development. There's modern Fortran that looks very different from old Fortran that people often think about when they say Fortran is not great. It's still widely used. Particularly in science and engineering, but also C++, of course. And then we have Amber Tools, which is a range of about 40 different programs. So that's a free distribution in the GPL that has all the preparatory and analysis programs for these types of simulations. And then there's Amber itself, which is the name for now basically the high performance MD program. It has an academic license, so it's actually not free. It's been licensed. It's sort of semi-commercial, but for any nonprofit, it's free under an academic license. And so these are the type of applications, biomolecular simulations of protein, DNA, RNA, lipid, sugars, all these biomolecules that are building blocks of cells and tissue that give us an understanding how life works at the nanoscale. And of course, also an understanding of biomolecular function and disease. And so it's often also used for computational drug design. So we can study things like enzymatic reaction mechanisms, stability of protein drug complexes, for instance. And it's used in part of some of the drug design pipelines. It's also very widely used. These are just some citation numbers. And the way I just want to give you an impression on how we can model molecular interactions. So either we use quantum mechanics and solve, how do the electrons in the molecules actually behave and move? So we can solve the Schrödinger equation or what's called density functional theory. Or we have a very simplistic approximation that basically represents the molecules as ball and spring models, if you want. So where you have like the, atoms here as balls connected to each other via bonds. And so you have these harmonic terms where you have, for instance, a bond in terms of the distance r between two of those atoms and the equilibrium distance. And then a similar thing for angles between three atoms and dihedrals between four atoms. And then there's electrostatic interactions there's charges on these atoms because the atoms are not neutral. So that maybe from water molecule you have a dipole moment, so the oxygen is slightly negative, the protons are slightly, the hydrogen atoms slightly positive, and other non-bonded interactions. And this looks complicated at first look compared to this, but here I'm hiding all the complexity, of course, in this Hamiltonian and the wave function of this is built. So these things are really expensive but highly accurate. So no chance you can do any simulation of a protein with some wave function methods here, quantum mechanics, like CCSDT. Force fields are very fast but not as accurate, and so somewhere we want some predictive simulations in between, and that's where AI can also help, and or mixed multiscale methods like QML. And so for molecular dynamics with classical force fields, so the simplistic examples, here's a study that I did in the past on cytochrome C oxidase, and you can really see how we can see how the whole molecule moves over time due to temperature. And in this case, we were able to identify pathways through which water molecules that are produced in a reaction in here in this enzyme actually leave. This cytochrome oxidase, C oxidase, all of you have that in your mitochondria. This is the final electron acceptor in the electron transport chain. So when you basically metabolize food that you eat and produce ATP. So this actually generates a proton gradient, and that proton gradient in the cell membrane is then used to produce ATP down there. And so on. And the relevant timescales that are necessary for the simulations are what we want to simulate is on the micro to millisecond timescale in terms of like life of a molecule like this. This is where we can extract some useful information about biophysics. Nanoseconds are useful as well. The time steps we have to use in this molecular dynamics simulations are femtoseconds. So we have to compute the interactions between these are hundreds of thousands of atoms. And so that's why it's very complex and complicated. Based on those interactions, we get the forces that are acting on the atoms that make the molecule move, and then we can do a numerical integration of those time steps of Newton's equations of motion effectively. And we cannot go to much larger time steps because of the speed of those vibrations in the molecules. And so hundreds of millions of time steps are required. And if we want our simulations to finish in a finite amount of time, so graduate student who's doing some of the simulations, right? He wants to finish after a few years and not after a few decades, right? So we need to do all those computations in under a millisecond wall clock time per time step. And so that's why we need these high performance codes. And if you implement this correctly, so these are old benchmarks, but the essence of this still holds. This was with the AMBER 18 release, 2018. This is the performance in terms of nanoseconds per day. So how many nanoseconds in the life of the molecule you can simulate in a day, so 24 hours. This was a benchmark of a cellulose strand here in water, about 500,000 atoms. The top of the line CPU node that we had, this 36 CPU cores, gave you about 2 nanoseconds per day. And our GPU implementation gives us an order of magnitude more, 20 to 50, depending on the type of GPU. Works very well also in gaming GPUs. I told earlier, they also have very high FP32 floating point performance, not so much FP64. So what we did is we first implemented SP, we call it single precision FP32. If you do this for all parts of your code, what happens is what you see here is the energy with respect to the starting energy of the system. When you don't have any thermostats applied, you're just solving Newton's equations of motion, energy must be conserved, otherwise something is wrong. And the physics you are describing is not going to be correct. And you can see that this simulation basically blows up, it heats up, it blows up because of numerical inaccuracy. So you cannot do everything in lower precision, right? You can do tricks though. And so currently what our code has is something where we do most of the computations in single precision, FP32, and then we do data accumulation actually in fixed precision, And that 64-bit fixed precision. And so that actually is very fast also on gaming GPUs and conserves energy. So you have to be very careful with numerical accuracy.
45.
I'm at my limit.
Yes.
I'm at my limit. So I will very briefly tell you what QUIC is, skip over some slides, and come to the conclusion. So QUIC is a quantum chemistry code. It does that Schrödinger equation solving thing. And that runs also on GPUs. Feel free to go to this website. It's an open source code. You can clone it and download it and play with it if you want, or contribute to it. We're happy about contributors. And it runs entirely on GPUs. It also runs on CPUs. So there's a range of papers where we have developed these methods over the last few years. And I will skip over some of the tricks that we do in order basically to have our computations parallelize efficiently. But there are some things like, for instance, we need to do a numerical quadrature where we have thousands of grid points on the molecule and where we have to integrate the electron density that is described due to the wave function of the molecule. And then what we're doing is we basically sorting the grid points, batching them into, with an octree-based algorithm, batching them into like batches of the same number of grid points. And then we can distribute these very nicely onto the different processing units of the GPUs. And because we have sorted them, the same types of work needs to be done on the same points in that batch of grid points. And so we don't have a thread divergence and so on. So we get a very, very nice parallelization with a good efficiency. It also scales well across multiple GPUs. So we have a multi-GPU implementation. And just want to show here, when we started in 2000, basically version 20, going down to 23, this is on the same type of GPU. This was just us improving and optimizing the code, starting with a baseline GPU implementation that was already quite efficient, but we got about 3.5-4x speed up simply by actually optimizing our code. And we can use this for mixed quantum classical simulations where we have a QM region and a classical region where we integrate the code with Amber. It's numerically accurate. It conserves energy. That was effectively the same thing that I told to you about the performance that has been increasing over time. And then, of course, also with the newer hardware, we get much higher performance. And so that enables us actually to do real science on GPUs for these QMML simulations. And I'm going to talk a little bit less about the computing and more about the simulations in the afternoon in case you're interested about that. This is all integrated in the Amber software package and Amber tools for doing multi-scale simulations and combined also with AI models, where we are using these quantum models to train and inform in AI models that then run faster. And we can use those for all types of simulations, not only reaction mechanisms, but also predict binding free energies, for instance, of drug-like molecules to proteins. And that brings me to the end. So the world of scientific computing is changing rapidly. So you have to think about heterogeneous computing already with CPUs and GPUs. Other accelerators are emerging. The GPUs in particular, and the AI accelerators, of course, have been driven by advances in AI and machine learning. And for computational chemistry, we have to work with this. I think there are lots of nice opportunities. In terms of QUIC, that's an open source multi-GPU capable quantum chemistry code. Please take a look if you have some interest in that. And QUIC and Amber as a combination gives us a very fast multi-GPU capable mixed quantum classical code that enables us to do simulations. The reason why we want to do QM, it can be more accurate. B, we can study reactions, which you cannot do with these simplistic force fields actually. So enzyme reactions, for instance. And with that, many people have been involved over the years in developing of these codes, both at scientific institutions. NSF has given us funding. We have great collaborators from NVIDIA, AMD, and Intel These are some acknowledgements also of NSF-funded systems, Cosmos system with the Cosmos APUs that I was talking about. And then thank you so much for your attention, and I'd be happy to try.
We'll probably have time for one or two questions. Yes, we have.
So you list a bunch of languages that people use for accelerators and whatnot. Which one would you recommend students learn first?
Recommend students learn first? That's a very good question. So I personally think it's actually nice to learn CUDA and or HIP. HIP is nice because in principle it works on AMD and NVIDIA GPUs. If you start with CUDA, you're stuck with NVIDIA GPUs. The reason is I don't think it's overly complicated, but if you understand the concepts, then it's also much easier to use pragma-based languages. Now, to get a faster porting, of course, if you have a CPU code, and it's in some sense also easier, is to use OpenICC or OpenMP. OpenMP, I haven't used it much. It seems to start to work actually reasonably well. So I think that's one thing. Now, if you're just interested about GPU acceleration and you have a Python code, you can also do that, but then you don't actually learn much about how GPUs work.
Yes.
So you mentioned, you used this word that the APUs, the fact that they have integrated memory, whatever, they are potentially faster, in multi-APU calculations. You use potentially because you haven't seen that yet.
So what I meant is, so the communication between the APUs is not faster than between the GPUs. Literally, that's exactly the same. So these APUs are called MI300A, but there's also the MI300, which is just a GPU. So if you just communicate between the GPU portions of the code, it's the same speed. Now, what you don't have to do is to transfer data from the CPU RAM to the GPU. So if you have a large code base and you want to port that, that is an advantage because you don't have that data transfer bottleneck between the CPU and the GPU.
Makes sense. Thanks.
And when you port in code and you start accelerating a portion of the code, you will see an immediate speed up and not a slowdown because first, you have all this data transfer and you have to. It probably makes the porting experience more fun for the developers.
Okay, there are no more questions. Let's thank Andy again. And